Max Planck Institute, and he will be talking about Anderson localization, topology, and interaction.
Okay, thank you.
Okay, so I will talk about various subjects which are all related by these notions, localization, topology, and some of them will also include interaction effects. And first of all, of course, I should thank the organizers. I'm very happy to be here in Cambridge. It's a very nice place, and thank you very much for organizing this nice meeting to participate for me. And so this is this talk combines results from two works which I did in collaboration with these with Igor Gorny, Sasha Mirlin, Vanya Protopopov, and our student Elio Koenig. And the most part of my talk will be the introduction. It's more than half of the whole talk. It does not contain any new material, but I just want to introduce the playground of some notions which I will use in my just something which was known before, and probably not everything is known to the audience. Okay, so the starting notion is the scaling theory of localization, which appeared, as it is believed now, due to the paper of the Gang of Four in '79. We already have seen this graph in previous talks, and what is shown here is the scaling of the conductance of a finite sample as a function of its size, and there are two limiting cases, either a metallic limit when the scaling is according to the Ohm's law, and the insulating limit when there is no conducting states in the sample and electrons just tunnel from one side to the other with the exponentially decaying conductance. So it can be drawn in the form of the logarithmic derivative of the conductance with respect to the logarithm of the size, and the two limits are, here is the metallic limit, here is the insulating limit, and metallic limit depends on the dimensionality. And for instance, in 3D, we see that this derivative changes sign at some value of g. This is the Anderson transition, while in 2 dimensions, the function seems to be always negative, so there are no metallic states in 2 dimensions, but it is approaching 0 as you go to a limit of large g. So it is still a question what happens here. Is it everywhere negative or not? And the answer to this question was given by the calculation of quantum corrections, which actually means that in the metallic limit we have Ohm's law, and there are some weak corrections due to non-classical motion of electrons. These corrections are related to self-intersecting trajectories of electrons. So if we have an electron which scatters of disorder and the trajectory intersects itself, so there is, for instance, an impurity which scatters it twice. Actually, it's a bit more complicated. Then there are 2 possible trajectories which go around this loop in the same or different direction, and the interference between these trajectories is gives the correction which is proportional to the probability of return to the same point for a random walk. And this probability depends, of course, on the dimensionality of the system and the corresponding probability. This integral diverges if we are in 1 or 2 dimensions, but it converges in 3 dimensions. So this correction, although it is weak due to small Planck's constant, it is divergent due to geometric reasons. The sign here depends on the spin symmetry. So if the spin is the conserved quantity, if electron spin is conserved during this work, then the correction is negative. It's called weak localization correction. If spin is not conserved, if we have spin-orbit coupling in the system, the correction is positive. So this is constructive interference, and this corresponds to weak anti-localization. And finally, if the time reversal symmetry is broken, then the phase accumulated along this loop is random and the interference is broken whatsoever. But there is a more sophisticated interference effect with two loops, and it again gives a negative correction, but smaller than here. In 2 dimensions, it is also divergent, but the prefactor is smaller than here. So all these results can be put on the graph. These weak localization corrections, they are due to at least these 2 papers, one of Dima Khmelnytsky, who is here in the audience, and these 3 situations with broken time reversal symmetry and preserved, but broken or preserved spin symmetry are now called orthogonal, unitary, and symplectic. I will explain later why they are called this way. So in orthogonal case, which is the most common, all symmetries are preserved, both time reversal and spin. The correction is negative, and it means that this curve deviates down from 0, and indeed there is no metallic state in this situation. In unitary class, this correction is again negative but weaker, again no metallic state, but in symplectic situation, when spin symmetry is broken, there is a positive correction, weak anti-localization, and it means that the curve should cross 0 somewhere, and again this is the localization transition, Anderson transition in 2 dimensions for a system of a symplectic class. Now these weak localization corrections, they may be calculated systematically, not only to the lowest order with diagrams which I have shown, but to any order using an effective theory which is called a sigma model. And sigma model, actually, it was also discussed here already a few times. It's a theory which, with this action, with a field Q being a matrix, and for these 3 cases, unitary, orthogonal, and symplectic, this matrix belongs to one of the 3 coset space shown here. Yeah, this theory, just if you do a perturbative calculation, if you assume that if you expand in this Q in series in some way, you will recover all the diagrams which you can calculate also directly without any sophisticated models. So this theory also assumes that you have to take the replica limit n to 0, n is the parameter, is the size of the Q matrix, and then renormalizing this action, you get corrections to D, which mean weak localization or anti-localization corrections. Then there is a more complicated situation in the system, in a 2-dimensional system without time reversal symmetry, which is called the quantum Hall effect, and experimentally it was observed by von Klitzing and co-authors in 80. The effect is that if you apply a magnetic field to a 2-dimensional system, the Hall conductivity gets quantized with a very good precision at some integer values, and the explanation is more or less like this. First, imagine there is no disorder in the system. You apply a magnetic field, then there are electron trajectories which are just circling here. They belong to some Landau levels, and on the edge you have a trajectory which bumps at the edge and goes around the whole sample. This is the spectrum. You have Landau levels, you have Fermi energy, and you, for instance, here 2 levels are filled, 2 levels are empty, but close to the boundary, these levels bends up, and your Fermi energy crosses 2 of them here, and these 2 are exactly the extended states which propagate along the edge. Now, if we introduce disorder, all these electrons in the middle of the sample gets localized. So these circles, they're pinned to impurities, they're immobile, but these edge states cannot be localized because they all propagate in the same direction, so scattering between them will never turn them back. So the longitudinal conductivity is 0 in this state, but the Hall conductivity is exactly 2 because we have 2 such propagating channels at the edge. And this can also be incorporated in the theory which I discussed before in the sigma model. If you add in the unitary class this specific term to the action. It was done first by Pruskin in '83, and this is a very specific term. It's called a topological term or theta term, and the nature of this term is the following. So Q matrix takes values from this coset space. So in some sense, Q matrix is defined in every point in our sample, and it maps the real space to this matrix space. Real space is equivalent to a two-sphere because we consider only configurations which are trivial at the boundary. So boundary maps to the single point, and mapping of a two-sphere to this manifold actually can have a non-trivial homotopy. There is a whole homotopy group Z. So there are inequivalent mappings which cannot be transformed one to the other, and this topological term is just an index which tells us in what homotopy class we are in. So it's a Hopf invariant in the sense that if you will calculate the variation of this action, it will be 0, but for different homotopy classes it takes different integer values. It is quantized in this fashion, and adding this term to the action means that first of all it's imaginary, and second, as we change sigma xy, the action changes periodically. So changing sigma xy by 1 adds 2 pi I times the integer number to the action. So the flow equation, if you renormalize this action, it's not so easy, but it was suggested by Dima Khmelnytsky that it should look like this. We have localization, sigma xx flows down to 0, but due to this term there are corrections which also change the value of sigma xy, and it flows either to here, either to 0 or to pi. Then it's a periodic picture in the vertical direction. So sigma xy always flow to an integer number in proper units. And there is a critical point in between, which is a quantum Hall critical point. If we have sigma xy exactly half integer, then it doesn't know where to which of the two quantum Hall plateaus to flow, and we have a critical state between two quantum Hall plateaus, which was discussed in particular by in the talk by Ilya Gruzberg.
So this is the normalization group flow.
Yes.
Explaining here. So does that? So you have sigma xy. So that actually will flow under the renormalization group. I mean,
It's a, in some sense, it's a non-perturbative renormalization. So the corrections to sigma xy are due to instantons which interact with, they do not, in the dilute limit you can, actually it cannot be calculated, it's just a sketch how it should look like.
That's why I was wondering whether you could,
Yes.
because renormalization
We cannot, but
infinitesimal thing and you would not see the motion of it.
yes, but we can calculate it somewhere far here in the weak coupling limit when
Yes.
sigma xx is large, and we can identify small flow in the vertical direction there due to instantons.
You can see some instanton, correct?
Yep. Well, not we, but other people. Okay. Then there is another similar topological effect, which is much younger. It's started only around 2005, which is called quantum spin Hall effect. This is a situation, again, when you have a two-dimensional system, but the time reversal symmetry is preserved. There is no magnetic field, although there is some spin-orbit coupling, so the electron spin feels some effective magnetic field depending on the velocity. If you drive a current through such a system, the current is due to electrons with spin up and spin down, and these two types of electrons, they feel opposite effective magnetic field. So spin downs, for instance, will deviate to the right, spin ups to the left, and you will have a spin current in the perpendicular direction. There is no net charge current, but there is a spin current. So this is called a spin Hall effect. This is a classical effect, nothing quantum on this picture. You have a system with spin orbit interaction. You pass the current in one direction, and you have a spin current in the perpendicular direction. Now, if this spin orbit coupling in the system is extremely strong, it might happen that due to spin orbit coupling, you open the gap in the spectrum, and the bulk of such a system becomes insulating. However, this spin Hall effect will still be present, so you can drive a current and see a spin current perpendicular direction due to edge channels, which will also appear in such a system. This edge channel will go in both directions, left and right, but in one direction with spin up, in the opposite direction with spin down. And this is called a quantum spin Hall effect. Again, the system is completely time reversal invariant. If you want, it's a combination of usual quantum Hall effect with magnetic field up and with magnetic field down in the same sample. And in the usual quantum Hall effect, it was quite easy to see that any scattering at the edge will not localize the edge modes because they are chiral, they propagate in the same direction, and this was the reason for robustness of the effect. And on the sigma model level, it was due to this topological term in the action. And for the quantum spin Hall effect, there is a similar situation. If you have an impurity which can scatter, which has some potential but cannot flip the spin of electron, it will also not scatter back the states because these two states have opposite spins. They are orthogonal in the spin space. So if you preserve time reversal symmetry, if you do not allow magnetic impurities which act on the spin, then this effect is also robust. And actually, I do not show this, but it can be described within a sigma model with a corresponding topological term in one dimension. So there is a specific sigma model just for the edge of this system, one-dimensional model. And this topological term is a Z2 topological term in the sense that in this situation there are only, the homotopy group is Z2, there are only two non-equivalent homotopy classes, and this topological term is either 0 or I pi, depending on which class you belong to. Okay, so this is the experimental observation of the quantum spin Hall effect. It's from 2007, and actually it's not as good as for quantum Hall effect yet. So this is the quantum well of mercury telluride and cadmium telluride. There is a layer of mercury telluride in between, and depending on the thickness of this layer, you can open a gap in the spectrum just by size quantization, and changing this thickness, you can have a system in the quantum spin Hall state with the H channels here and there, and measuring just the DC conductance, two terminal conductance, you will see a quantization. Conductance equal to 2 squared over H means that you have exactly two channels in the system, two conducting channels. Okay, so all these situations belonged to one of the three situations which I called orthogonal unitary or symplectic so far. This is the symplectic case, strong spin orbit interaction with time reversal symmetry. And actually there is a more general symmetry classification due to many people, but mainly due to Altland and Zirnbauer. This is the exhaustive classification which tells us what are all possible symmetries of disordered systems and what are the consequences of the symmetries. What was discussed so far was the time reversal symmetry. Time reversal symmetry means that the Hamiltonian is related to the transposed Hamiltonian by some similarity transformation. This operation T, which is called time reversal operation, applied twice should bring the system back to the initial state, but the square of time reversal might be either +1 or -1. +1 means orthogonal class, -1 means symplectic class. No time reversal symmetry means unitary class. And there are specific modes which are called Couperons, which is an average of a product of retarded and advanced function, and this mode appears in whenever you have time reversal symmetry, and it is included in the sigma model. There is another mode which is called diffuson, which is always present irrespective of any symmetry, just because of the conservation of the number of electrons. But as was realized by these people, there are other symmetries, namely a chiral symmetry or a combination of chiral and time reversal symmetry, which is called particle hole symmetry or Bogoliubov-de Gennes symmetry. And these symmetries may lead to a new soft mode in the systems, namely a diffuson composed of two retarded functions appears when you have a chiral symmetry, or a Cooperon of two retarded functions appears if you have a superconducting symmetry. This is quite easy. You just take a diffuson, which is always present, and you apply one of the symmetry operations to one of the two green functions. Chiral symmetry, by the way, is the relation between h and minus h with some unitary transformation, and this CT symmetry is the combination. So h is related to minus h transposed. Now we can compose the whole list of all possible symmetries. There are exactly 10 situations. So this column tells us if we have a time reversal symmetry and is it real or imaginary. Chiral symmetry cannot have any particular sign. It's either present or absent, and this Bogoliubov-de Gennes symmetry may have a sign. And the first three situations, which are unitary, orthogonal, and symplectic, are first three rows of this table, and they are described with a sigma model which lives on one of these three coset spaces. And there are 7 other situations. 3 are called chiral classes. This is chiral unitary, chiral orthogonal, and chiral symplectic. And there are 4 superconducting classes. And this, in some sense, exhausts all possible symmetric spaces with unlimited size, excluding there are some more which are not scalable.
Do they play any role in physics?
Not in this. So far, not in this physics. In some other physics, they do.
Thank you.
Okay, and in some sense, this proves that there are no other classes because we have already exhausted almost everything. And here I list also the homotopy groups of these spaces and weak localization correction in one loop, just lowest order. It's weak localization, negative correction in orthogonal class, positive correction in symplectic class, 0 in unitary class, actually negative but in next order. And what is interesting is that in the chiral classes it's also 0, not only to the lowest order but to all orders. I will discuss this a bit later. And these homotopy groups, which are also known, tell us in which situations we can add topological terms to the sigma model. So we can now generalize this quantum Hall and quantum spin Hall to all classes, to all dimensions. We can just tell in which situations there are topological effects. There is a possibility of topological effects. And first, to do this, we can reorder. It's the same table, just rows are reordered in a different way. It's a very clever way of ordering. You see the ones here are now arranged in a very nice fashion. And with this ordering, the homotopy groups are periodic as you increase the dimension. And there is an 8 periodicity. Pi 1 and pi 9 is the same for all classes, and then they shift by 1. This is called Bott periodicity, and probably for mathematicians it was known for 60 years, but somehow it was introduced in this field only in 2008 in physics, and nobody knew about it before. And now it's very easy to do this classification. It is called a classification of topological insulators. Classification is very easy. Whenever you have Z in that table in some dimension, if the homotopy group is Z, it's the situation analogous to quantum Hall effect. You can add a topological term to the d-dimensional sigma model, meaning that d-1 dimensional surface states are delocalized, like H states in quantum Hall, and this is a d-dimensional Z topological insulator. Whenever you have Z2 in that table, it means that the situation is analogous to quantum spin Hall effect or to the surface of 3D topological insulator stated here. So you can add a topological term which is either 0 or I pi, and you get absence of localization in so you get a topological insulating d+1 dimension of a Z2 type. So this is like quantum spin Hall effect. In 2 dimensions, we can have this because pi 1 equals to Z2, because we can write a sig model for an H, because in symplectic class by 1 equals Z2. So we can do it for all other classes, for all other dimensionalities. Okay, so this is again the same table, but now I write not the homotopy group, but I shift Z2s by dimension 1, so I can directly list what are the possible topological insulators. Quantum Hall effect, for instance, is here. It's 2 dimensions unitary class. We have Z. Quantum spin Hall effect is here, 2 dimensions symplectic class, Z2. There are 2 other variants which are called spin quantum Hall effect and thermal quantum Hall effect in 2 dimensions. They are not really observed in the experiment. For instance, this thermal quantum Hall effect was discussed by Shinsei Ryu in his talk 2 days ago. There are 1-dimensional examples which are realized experimentally, so in class D in some indium antimony wires, and there is this famous bismuth antimony or bismuth tellur 3-dimensional topological insulators, which I do not discuss in this talk. They belong here. And you see there are many other possibilities yet not discovered or discussed. Many things to do. So this is the end of my introduction. And now I will discuss 2 related problems. The first one is the localization in chiral system. As I told you, in 3 chiral classes in 2 dimensions, weak localization corrections are absent to all orders, and we wanted to understand what it actually means. So it's just a picture. Chiral symmetry means that the Hamiltonian anti-commutes with some unitary matrix. It means that you can find a basis in which the Hamiltonian is the block of diagonal matrix itself. So your system should break up in 2 subsystems, red and blue in this case, such that you have matrix elements in the Hamiltonian only connecting red to blue, but not red to red or blue to blue. And it can be realized, say, in any bipartite lattice with a random hopping. For instance, this is a bipartite lattice with 2 sublattices and hopping only between sublattice red and sublattice blue. Now I can introduce disorder in the system. I will just remove sides from the lattice. As I remove sides, I do not break the chiral symmetry because still I have red and blue dots and they are connected to each other, but not red to red or blue to blue. And if I remove sides, at some point the system will break in parts and will be insulating after this. So it looks like I should have metal insulator transition as I increase the degree of disorder, although weak localization theory tells us that there are no weak localization correction at all. So there is no any precursor of this metal insulator transition from the metallic side, which is quite strange. And actually there are a few numerical papers.
Are you saying that's a first order transition?
Percolation is not a first order.
No, percolation is not, I understand, but I thought you said there was no precursor.
Precursor, I mean that the conductivity should somehow drop. I want it to be second order. I want the conductivity continuously drop to 0.
Understand, yes.
Actually, it does, even in the percolation physics.
Yes, of course.
But the question is, do we have any quantum corrections to this? So in a classical system, yes, we have a percolation transition. In a quantum system, I would expect that when we are close to this percolation transition, interference between few trajectories left should somehow influence the conductivity. If it will not, it would be a very strong statement. So if a quantum system behaves exactly like a classical system, it's a strong statement. And if you calculate perturbatively corrections when disorder is not very strong, you don't see these corrections to all orders. They are absent to all orders. I will explain this in a few slides. Okay, so there is a numerical experiment within some network model for chiral class due to Bouquet and Choker, who really found, so alpha and gamma, some parameters of the model, they have really found a very short proof that there are no weak localization corrections. Again, this is a sigma model for the chiral class. There are 3 chiral classes, unitary, orthogonal, symplectic, with these spaces for the Q matrix. And it is exactly these 3 classes when you can add an extra term to the sigma model, which is not a trace of something, but is trace squared. And this term appears because the determinant of the Q matrix is not 1, it's a dynamical variable. In all other classes, it's either 1 or -1, but it's not changing. And now when you do renormalization, you have to renormalize these both parameters, sigma and C. And renormalization of C is related to density of states in these classes. And you can easily do the following thing. You can rewrite the Q matrix as a product of the e to power I phi times a new matrix U, such that determinant of U is 1. So you can single out this phase, which is the determinant, which determines the determinant of the Q matrix. And these 2 variables, phi and U, will decouple in the action. You will have a separate thing for U and a separate Gaussian action for phi with a prefactor sigma plus NC here. Now, since this is the Gaussian action, to whatever order in your renormalization group, it will not renormalize. So sigma plus NC is the integral of RG flow. And now if in this equation I take the replica limit n to 0, I immediately recover that sigma is not renormalized. This is the argument due to Gade and Wegner from the beginning of 90s. Localization corrections are absent to all orders in perturbation theory, so this normally such calculation is done in the limit of large sigma as a series expansion in 1 over sigma, and all terms of the series expansion are zeros. So we have the apparent controversy. On one hand, we almost believe that strong disorder should localize the system due to numerical result and due to our intuition. On the other hand, we have no traces of this localization from metallic side. And if there is no localization, then what do we call topological insulator of a chiral class? In that table, I have chiral classes with some non-trivial letters. And I know that it should correspond to either localized or delocalized states in these classes. But if they're always delocalized, there is no way to make a topological insulator. So the solution to this controversy is the following. We have to make a non-perturbative renormalization of the model. And exactly due to this phase phi, which appears in the chiral classes, it is possible to introduce a very specific vortex excitations in the sigma model. A vortex means that this variable phi changes by 2 pi when you go around some point, and this point cannot be eliminated. It's somehow topologically protected, although in the middle here there is a singularity of the field. The gradients diverge. And this situation recalls, actually it is identical to the situation of Berezinski-Kosterlitz and Thouless transition. And this is just 2 slides about what is Berezinski-Kosterlitz-Thouless transition for those who are not familiar with this. It's exactly the renormalization of the Gaussian theory just for a variable phi, like here. Phi lives on the circle from 0 to 2 pi. There is no perturbative renormalization, but if you allow singularities in the field, which are vortices, you can associate some energy with the core of the vortex as core, and then there are 2 phases. There is a low temperature phase when you have these vortices, they are logarithmically interact and they bound in tiny dipoles if the temperature is low, and this is the ordered phase with a long range order. At high temperatures, vortices unbind, and you have vortex plasma or disordered phase, and the behavior of the system can be described with these 2 RG equations for J, for the parameter J, which is called stiffness, and for parameter y, which is called fugacity, which is related to the energy of the vortex core. And this is the flow diagram. You have a blue phase, which is ordered, and white phase, which is disordered. Is it the end of my time?
I have 1 minute.
1 more minute. Well, I have only 2/3 of my material. Okay, now very fast. We can include these vertices in our sigma model, and these are the equations that we have. They're not exactly like Berezinski, Kosterlitz-Staulis transition equations, but we identify a negative correction to conductivity, which means that vortices lead to localization. This is the flow diagram for our equations. We have metallic and insulating phase here with some transition between them. And actually, this is at least a three parameter scaling diagram, so it's very different from what was initially proposed by the gang of 4. There is no minimal metallic conductivity in this case. And we can also introduce topological terms now in this model, and which will bring us an instantons, and we know how these instantons interact with vortices, and we can identify the topological insulating phases now. So we have localization due to vortices, or absence of this localization due to additional topological terms. Okay, now this is the third part of my talk. About the localization in symplectic system. This just literally very easy. There are additional soft modes when you have an interaction in the system, which are called plasmons, and you can also include them into the sigma model, which was done by Sasha Finkelstein. And they will change the weak localization corrections, so they will introduce, apart from weak localization corrections, also Altshuler-Aronoff corrections, which are also logarithmic, and there is an interplay between them. And in particular, in symplectic class, where before we had a metal insulator transition, due to interaction, there is no metallic phase anymore, and the system is always insulating. And this can be applied to the quantum spin Hall effect. This is the phase diagram for the quantum spin Hall effect, which I discussed in the very beginning. There is a quantum spin Hall insulating state with H modes. There is a state without H modes, normal insulator, and there is a metallic phase between. And this line is the metal insulator transition in a symplectic class, which was known due to papers by Hikami, Larkin, and Nagaoka. And now if we introduce interaction here, we kill this metallic phase due to Altshuler-Aronoff corrections, and we have a direct transition between normal and quantum spin Hall insulator with some critical state in between. Nobody knows what this state is so far, but there is a very important point that in symplectic class it is also possible to introduce vortices. The corresponding homotopy group is not Z but Z2, so these are Z2 vortices. Vortices which are equivalent to anti-vortices. Still they can be introduced, and this is what was proposed in a very recent paper by Fu and Kane 1 month ago. That actually the metal insulator transition in symplectic class is due to Z2 vortices and not happens without them. So they introduced a very similar phase diagram to what we had before for our Berezinski Kosterlitz-Staulis transition in the sigma model. They have the fugacity of the vortices, and if there is no vortices, the system is always metallic. And now there is a proposition, it's just a proposition, it's not a result, but very promising. Now we can combine everything. In the symplectic class, we can combine vortices and Coulomb interaction, and this will be a proper theory for the critical state of the quantum spin Hall effect. So if Coulomb interaction will kill the metal phase, if we also remove vortices, if this is true, we have no full localization, so we will get some critical state there. Okay, so this is list of my conclusions, and thank you for your attention.
Your previous slide, if you turn this phase diagram, it's looking somehow familiar.
Turn which direction?
The vertical, it is looking quite familiar.
Is it a question or statement?
Whether there are some reason for that, I mean.
You mean why the up and down is the same?
No, I mean, that similar kind of phase diagram you get when you have some large N or whatever, just you see that there's something when your V is non-monotonous and T goes to either just insulating or super metallic behavior. Whether there is some reason for all that? I mean, connection with the previous kind of behavior.
First of all, I still do not quite understand the question.
Okay, well.
But this picture is, in this context, is the same picture as we had here. It is this one, so what we call y, they call v, and just they plot it in two directions. We can also plot it from negative y to exactly the same. But it's similar again to Berezinski-Kosterlitz tablets. They also can have positive and negative fugacity. I don't quite understand to what you try to
No, I
compare
think that
this.
I thought that V is interaction. So that,
No, v is fugacity.
okay, then it's nothing.
If not, let's thank Pavel and all other speakers of today's session.